Professor of Engineering and Finance at Princeton University in the Department of Operations Research and Financial Engineering. He will speak today on mean field reinforcement learning with common noise. Please, Rene.
I'm sure you're not going to take me very seriously, but I really apologize. And I'm very sorry that I'm not in Montreal right now. I wanted really bad to do it, but didn't happen. So I'm going to talk about something maybe or definitely simpler than what Pierre has been talking about. It's not going to be about mean field game per se, but there will be mean field and even common noise in the model. We're going to look at discrete time. So all the tool of stochastic analysis are mostly out the window. And we're going to try to look at learning issues. In other words, not being able to know all the coefficients of the model and still trying to find an optimal solution. So this is a joint work with Mathieu Laurière and Zongjin Tan, started a long time ago. So we originally posted on arXiv a paper where we were looking only at closed loop controls, closed loop policies, Markovian policies, and stationary policies. You know, while we were trying to polish the paper for submission, Yun Pham and Mot posted and actually published a paper where they were extending what we did to the open loop case. So before deciding what to do with our paper, we looked carefully at this paper of Mot and Pham, and we realized that what we would have done had we decided to do the open loop case would have been slightly different and the result different. So we decided to start almost from scratch and rewrite this paper posted on arXiv to include the open loop case as well. What I'm going to try to do is present this new paper, which is only recently submitted, even though the original version was, I don't know, 4 or 5 years old, I don't remember. Deal here is to try to learn optimally and to control optimally a dynamical system which is in discrete time. So the elements of the model will be a state space, and to do some reasonable mathematics, we'll assume that it is a Polish space, an action space, A, which will also be assumed to be a Polish space, then a sequence of idiosyncratic random noise. So this will be a sequence of random variable, independent, identically distributed, possibly taking value in the Polish space as well. A system function, which is going to basically define the dynamics. And for that, we use the same framework as Mot and Pham. Usually in reinforcement learning, the dynamic of the system is given through a transition kernel rather than a system function. They're not 100% equivalent, even though in spirit they are, but we're going to stick to the approach based on the system function, which is a function of the state, an action, the random shock, and give a new state. Okay, and we will try to control the system through control processes, which are stochastic processes with discrete time parameter, but with value in the action space. And we'll also have an initial condition. Most of the time, we will assume that it is random and distributed according to a probability measure μ0 on S. And the state dynamic will be given indeed by this state function, this in the form that the next state will be this function capital F of the previous state, the value of the action taken by the controller, and the idiosyncratic innovation. The optimization will be based on a one stage cost function, which will be a function of the state and the action. And the goal will be to minimize the infinite horizon aggregated cost, discounted cost, discounted with a discount factor, which we'll assume is strictly between 0 and 1. Okay. What is reinforcement learning? Reinforcement learning is simply trying to compute either the value function, namely the infimum over all the action processes of this expected cost, or trying to find directly an optimal stochastic process giving an action process realizing the minimum. However, we will assume that we do not have full knowledge of the coefficient, and so de facto we will have to work with approximation of this optimal solution, if any. We're going to learn, and usually we learn either from online data, getting online, or from batches of data which have been collected in buzzword in reinforcement learning is, and I will use it only at the end of the lecture, is to try to strike the right balance between exploration and exploitation. And this is because we're going to use iterative algorithm to try to overcome the fact that we do not know the exact function capital F and little f. The most famous of these approaches to find still the optimum value and the optimum control is the tabular Q learning. And we'll mention and we'll use several generalization of this Q learning. It is very simple, very intuitive, and very efficient when the state space S and the action space are finite. And in fact, when they're small, when they're large, when they're very large, it is not as efficient. Just a couple of references to differentiate what I'm going to try to do from what is very often called mean field multi-agent reinforcement learning, whereby we have an agent, and this agent choosing a set of policy pi 1 pi n, this policy giving them actions alpha 1 alpha n. I will define these terms precisely momentarily, but the agent compete, and the agent try to maximize their own award, and so there is no cooperation between the agent. And so in this literature, most people try to find Nash equilibria. I think the standard paper in this area is a paper by Hu and Bellman in 2003, where they call Nash Q Learning. Each player basically construct their own estimate of their own Q function, making guesses for the Q functions of the other players. The Q function is the state control value function, which we'll introduce later on. But then in this approach, they try to find Nash equilibrium. It is computationally extremely involved. It is suffering from the usual problem with Nash equilibria, and in particular, lack of uniqueness. More directly, there is a huge literature on learning mean field games. And so I cite here a certain number of papers, and they are based on generalization where the players have different types, where maybe some methods try to find a Nash equilibrium at each stage, which I find personally quite unnatural in many applications. They split the time into a short period, and then they try to use fictitiously to reach Nash equilibria. The second set of references here are people from Google Brain, and more recently, Anguilli, Fouque, and Laurier tried to basically bridge this approach in learning on mean field game with the learning for mean field control, which is what I'm going to concentrate on. What is the actual problem that we're going to look at here? We're going to have centralized policies, centralized control processes, as opposed to distributed one, like is often the case in mean field games. And typically, you could imagine that you want to control a set of N drones flying over a certain region S, and trying, for example, to detect object, say mines, okay? And at each time N, we can imagine that the drone communicate with a central unit. So they broadcast their position, their states, their how successful they have been in identifying mine, how many and where they are, etc. And the central unit will aggregate this information coming from the N drones, do some sort of massaging of this information, do the optimization, find a policy which is optimal for whatever the central unit is optimizing, and then dispatch this policy to the individual drones, and basically requesting that they implement this policy, they use this algorithm to take their next move, okay? So in the limit of n tends to infinity, we expect that we will have some form of propagation of chaos, and that the state of the generic drone will be given by an evolution of the type that we're describing before. And I apologize, we shouldn't have a term here, okay? And so we will have to find now a control problem for the central planner. And when the central planner dispatches the policy that he or she identifies, the agent will cooperate in the sense that they will not compete, and they will apply this single policy found by the central planner. And that's the type of problem we're going to look at, okay? So more notations, okay? So we're going to have a state space, an action space A. Now, we're going to have dependence on the joint distribution of the state and the action. So this will be an element of the probability on the cross product of the state space and the action space. And then we will have a function of the random shock. And so the state evolution will be given by a function of all these elements. We will have, again, one stage cost, which will be a function little f of x alpha, and again, this joint distribution of the state and the control. And if I denote by x in the position or the state of the drone I at time n, the evolution of the state will be given by an equation of this form, where the interaction is mean field. In other words, the interaction will be through the empirical measure of the the empirical measure of the couple's state control, right? and where, these epsilon i's are these idiosyncratic noise. The central unit will try to aggregate this information. This is this 1 over n, the sum j from 1 to n, and compute the expected cost throughout the infinite horizon due to the behavior of these drones, and will try to minimize this quantity. Okay. So again, if there is a mean field reinforcement learning coming from the propagation of chaos, the formulation of the problem will be to try to minimize over the common policy identified by the central planner this expected cost over the entire infinite horizon, under the constraint that the state at time n+1 of a generic drone is given by this function capital F, the system function applied to the state at the previous time, the action take at the previous time, and the joint distribution of the state and the control, of course, now with the innovation given by the random idiosyncratic. Why do I want to add common noise? Well, clearly, of course, in economics problem, the common noise is extremely natural, but also in physical application, these drones are flying in the same atmosphere. They're facing the same winds, tailwinds, headwinds. They are having the same difficulties, imaging the ground to detect the images. So this common environment is a random noise, which is common to all the drones. So we would like to include this common environment. So on the top of the idiosyncratic noise, which is denoted by E, we're going to add a common noise, which will be denoted by E0. So we have basically the same equation now, except for the fact that the dynamic of each drone is influenced by the random shock, which are idiosyncratic due to their own physical equipment, their own trajectory, but also the common noise, which is facing and affecting all the trajectories of all the drones. Again, we're going to try to justify the formulation of the problem, the actual mathematical problem we're going to tackle, by taking a limit n tends to infinity and appealing to a form of the propagation of chaos. But in this case, it is clear that while the idiosyncratic noise will average out, the common noise is not going to disappear. And the form of the law of large number, which was introducing the joint distribution of the state and the control, will now lead through a form of a De Finetti theorem, conditional distribution of the joint distribution of the state and the control, but the conditional distribution given the common noise. So that's the only twist in the problem. This is going to be a reinforcement learning problem where it is not mean field through the joint distribution of the state and the control, but the conditional distribution of the state and the control conditioned by the common noise. So I will not worry about justifying this informal limit. I think that Mote and Pham did some effort, took some effort to justify this rigorously. So this is the problem I am going to tackle, but I will need more notation and more definition to justify the differences between our approach and the approach of Mote and Pham, and justify and explain the differences in the result we obtain. So a policy in reinforcement learning is a function, and I'm not going to worry too much about the starting space from which this function is defined. We'll take care of that later. But it's with value in actions. Okay, so a policy, it's a sequence of functions giving from whatever argument giving an action, namely an element of the space A. A policy is pure if it takes value in A. Okay, so and the actions are just the value, the evaluation of this policy function. The policy is mixed or randomized if it is taking value in the set of probability measure on A. So if you have a mixed policy, and most of the work in reinforcement learning is done with mixed policy, because very often there doesn't exist optimal in pure policies. Well, we know that it's easier to find optima with working with the mixed policy. But if we're using mixed policy, when it comes to take an action, the agent, the robot, the drone will need to sample from this distribution, because now the value of the policy is only a distribution. So there is a sampling procedure which will need to be implemented to draw a realization from this probability measure. The policy giving only a probability measure, we want an action to compute the next state. So we need to sample from this distribution. Okay, a policy is open loop if it is a function of the past history of the sources of noise. This is the definition used by Mote and Pham. And I repeat, in our original work, we didn't worry about that. We worry only about a set of Markov policy. So now I am going to work on the same footing. But now, sorry, a policy is going to be mixed and open loop if it is a function of all the sources of randomness. So I add to the sources of randomness coming from the idiosyncratic noise and the common noise, the randomness needed to sample from the mixed strategy. I repeat, the mixed strategy do not give directly action. They give probability over the space of action. I need to have a process to sample from these probabilities, and I want to include this sampling procedure inside the definition of open loop strategy when the strategies are mixed. So that's the main difference with what Mote and Pham have done. And now, we'll call a closed loop strategy a strategy where the action, the value is only a function of the state visited from time zero to the previous time. And we're going to say that the closed loop is a policy is a closed loop policy if it is not only a function of the state, but the conditional distribution of the state. Okay, it is Markovian if it is only a function of the last state and the last distribution, conditional distribution, sorry, and it is stationary if it is closed loop Markovian and the function doesn't depend upon it. So all this list of definition and notation mostly to emphasize the fact that in reinforcement learning, typically people are working with, and there are good reasons for that, working with mixed strategy instead of a pure strategy. And this mixed strategy, require a sampling procedure, and I want to include this sampling procedure in the definition of open loop. Otherwise, does one sample from a mixed policy? At each time n, the player will look at the policy and will draw a sample from this policy. But now I'm coming back on the definition of this conditional distribution. And in the work of Mote and Pham, they condition only by the past of the noise term, idiosyncratic and common. But now, naturally, I will want to, when I'm dealing with mixed policy, I will want the conditioning to be done with respect to not only the past value of the idiosyncratic noise and the common noise, but the random phenomena, random mechanism I use, the coin flip I use to sample from the mixed policy. And then there is even an extra twist, is that there are two possible levels of randomization which need to be considered in this situation. Because, as I explained, we have this individual agent, think of the drones, and then we have the central planner, the central unit. And both will want to use mixed strategy. And so there will be a set of random mechanism sampling from the distribution at the level of the individual agent, the drones, but there will also be a mechanism to randomize the strategy at the level of the central planner. In other words, working in mixed strategy, the central planner will optimize and find a mixed strategy. So there is here for the central planner a sampling procedure, so a mechanism to generate a random variable from a measure. It distributes this policy to the agent, which in turn will also be facing measures, and they will have their own mechanism independent for each agent to sample from the mixed strategy identified by the central planner. Okay. Now, in this propagation of chaos limit theorem, the idiosyncratic randomization will disappear, but not the central unit randomization. Okay. So the probability measure P0 of xn alpha n, which appear in the dynamic of my state, it will be like in Mote and Pham, a conditional distribution conditioned on the past of the common noise, but for us, it will also be conditioned on the randomization used by the central unit. Okay, so it will be conditioning by something slightly different than what Mote and Pham. All right, so now we have a dynamic of the McKean-Vlasov type. The state at time n+1 is a function of the state at time n, an action alpha n, a measure which is the conditional distribution of the joint state control with respect to the sigma field I just mentioned, and then to innovation. Okay, so what we do typically when we study control problem of this type of McKean-Vlasov dynamic is that we lift the problem one level, and usually when there is no common noise, we end up with a deterministic dynamical system in which we can control and optimize. When we have a common noise, like in the present situation, we're going to see the idiosyncratic noise disappear, but we'll still have a random dynamical system at this level. To be specific, the new state space now is going to be the space of probability measure on the original state space. The new action space is going to be, and this is another difference with the work of Mote and Pham, is going to be now a probability measure on the product state action. However, this will introduce a constraint, namely state, which is the distribution of the original level 0 state, has to be the first marginal of the action. The action, which is now a probability measure on the product S cross A, its first marginal has to be the state, namely the distribution, the marginal distribution of the state. So that will impose a constraint. Not all the probability measure on the product are okay with us. The only admissible one will be the measure, the probability measure on the product for which the first marginal is given by the state. So that's a constraint. The new system function, we're going to define it as a function from the new state space, S bar, the new action space, A bar. The only noise innovation, which will be now the common noise, and will give as a result a new state, which is a new probability distribution on the original state space. And we will obtain it in such a way that we want the conditional distribution of the new state be given by this F bar of these elements. And so we're going to define it by pushing forward the joint distribution of X and alpha into the by the original function capital F. An initial state will be an initial condition for the original dynamical system. And now the dynamic equation is given by the system function F bar, and the one stage cost is defined similarly. It's going to be a function from the new state space cross the new action space, and it's going to be given by this integral of the original, cost little f, if we integrate that over the probability distribution, which is now our action A bar, okay? And of course, the goal is to minimize the discounted infinite horizon cost given by this new function little f bar. And we denote this by J of A bar, if A bar is a process of action. So now we are faced, except for the fact that the process of action could be depending upon the past. This is a typical, what we call MDP, Markov decision process, okay? Because we have a state space, an action space, an innovation given by a sequence of independent random variable, and a cost function, which is giving a cost for each stage of the evolution of the dynamical system. So this is, in a sense, classical, and there are an enormous literature, and I don't think I wrote it, but a very clean mathematical source is a book of Tsikas and Shreve, and I believe this was mostly the thesis of Steve Shreve, but they have a little book which is extremely well written, extremely detailed from the measure theoretical point of view, and one can piggyback on this book to tackle the problem of this lifted dynamical system and the optimization on this lifted dynamical system. And if we make, for example, the two assumptions stated here, H1 being that the new system function is continuous for each fixed value of the common noise. So if you fixed the value of the common noise, which could be, it doesn't have to be a real number. It could be any value in any Polish space, but the function f bar is now a function of a state, which is a probability measure, and an action, which is also a probability measure. So it makes very good sense to assume a continuity assumption here. However, I emphasize the fact that this assumption on f bar could be derived from properties of the original system function capital F, but making an assumption on the continuity of the original system function capital F, fixing the common and the idiosyncratic noise, will imply the continuity of the system function F bar, but it will not be satisfied, for example, when the state space and the action space are finite. Okay? So that would not be the right type of assumption you would want to make if you want the assumption to be made at the zero level, at the level of the original dynamical system. Okay. The second assumption we're going to make is that, well, we will not use it all the time, but when we want to identify optimal strategy, optimal policy, we will want to do that using some form of selection theorems, and it will be convenient to have the state space S and the action space A to be compact. I repeat many of the results and some that I'm going to state, and I'm not going to state many because they're highly technical, not from the PDE point of view, but from the measure theoretical point of view. They will not require this compactness assumption. But under these two assumptions, if I limit the policies to Borel measurable policy, then value function for a specific is lower semi-continuous, and even the optimal value function, namely the infimum over all the Borel measurable policy, will be lower semi-continuous. Okay, and under the compactness assumption, namely assumption H2, there exists an optimal Borel measurable stationary pure strategy. However, caveat, namely, this is a pure policy for the level 1 dynamical system. The optimization problem lifted. This type of policy could be viewed as a policy at the level 0 from the original reinforcement learning problem. But then for that original problem, it is still a mixed strategy. No way out, because there are cases where there is no existence of an optimal strategy. The second result that we prove, and I will cite, is that if we look at open loop policy, which are mixed randomized for the original problem, if we look at closed loop policy, which are randomized mixed for the original problem, the optimal value functions are equal, and they are also equal to the value obtained for the stationary policy identified in the previous result. Okay, so that's slightly different than the result of Mote and Femme. The main difference is that we have a slightly different problem because we are conditioning by a different sigma field. We have an extra source of randomness allowing the central planner, allowing the central unit to use randomized strategy. This result is similar to theirs because they are working only on value function. But as I want to emphasize, and I will not try to go over the first boxed result here, but mostly the corollary of this box is that under the assumption H1, so simply the continuity of the system function and the boundedness of the one-stage cost, we have a one-to-one correspondence between the policy at the level 1 of the lifted dynamical system and the policy of the original dynamical system, with equality of the value function in their respective dynamical system. So beyond comparing only the value function, we actually constructing correspondence between policy when we have that one optimization problem, the optimum is attained, we will have the same thing for the other problem. However, what is pure at the top level is not pure at the lower level. It is pretty risky to pretend you're working on reinforcement learning and do not do actual numerics. So the solution of reinforcement learning problem is most of the time based on the construction of the space action value function and for a dynamic programming principle for this state action value function. So what we do is first look at this lifted Markov decision process and prove a dynamic programming principle for this lifted dynamical system. And so for that, we use traditional ideas, traditional method. There is nothing original here. We just have to do very careful bookkeeping to make sure that everything was defined is measurable. You define the Bellman operator. It is defined in terms of a supremum. You want to make sure that this supremum gives you a measurable function if you work in spaces of measurable function, while this supremum is over not a countable family, but over a continuum family. So as I said, this is standard business, but we have to pay attention and we need to go through universally measurable function spaces of such function, and then try to check that our Bellman operator actually leave invariant the space of Borel measurable function, etc., etc. But then if we want to do actual numerical application, as I said, we have to work with the state action value function, which is defined as, again, for the lifted dynamical system as one step cost. So this is the cost for one step. And then from the second step on, we use a given policy. So the state action value function depends upon the policy. Okay, and this policy, you apply it from the next time on to get cost in the future. You aggregate them over time, you discount them, aggregate them, and compute the expectation, and you add the initial cost, this function f bar, sorry. So that's the definition of the state action value function, which is easily defined for the top level. Again, we can define a Bellman operator. This state action value function is the fixed point of this Bellman operator, as long as you pay attention to the measurability issue, and you can actually show that it is the unique fixed point of this Bellman operator defined on the space of bounded universally measurable. Okay, so we have now our state action value function, and we have a dynamic programming principle for the state value function only, and from that we derive a dynamic programming principle for the state action value function, because indeed the state value function is connected to the state action value function by this identity, which is okay for any pure stationary Markov policy. Okay, and now if we want to implement numerical method using this state action value function, this Q function, we can try to implement the Q learning introduced over 20 years ago, state and action finite. And this was done by Guo and Ao in at least maybe not completely a paper with complete mathematical proof, but at least with the idea. However, even when the space A and the space S are finite, we are working with probability measure on the space S and probability measure on the product. And so we need to basically handle the fact that now we are not on a finite state space because we are on these two simplexes, but it is not difficult to approximate measures through combination of Dirac measure computed on a grid and then project when needed to remain on a space of probability measure with a fixed finite support. We can also, and we do in the numerical implementation that we give in the paper, use this Pdpg algorithm. And this algorithm is based on, so stands for deep deterministic policy gradient, where basically you use two approximation, one approximation of the Q function, one approximation of the policy giving the Q function, and then you iterate. This is a generalization of a method that is well known in reinforcement learning, which is called the actor-critic algorithm, where you alternatively optimize the Q function, namely state action value function for a specific policy. So you keep the policy fixed and you optimize Q. And now, given Q, you now optimize pi. And for that, you use two neural network and you iterate that. And this is what is called this DDPG method, which we use systematically. We could also try to go to continuous state and action space, and we implemented some of these models. I will give maybe one quick glance at this, at one such model. And what we have to do is approximate the space of probability measure by replacing each measure by a histogram, basically, or which is a form of density estimation, and then working with finite approximation of these measures. So the first example which I give is an example which I think was introduced by Ben Soussan and Kolokoltsov for an example of mean field game on a finite state with 4 elements. But we're looking here at the analog of the mean field control problem instead of the mean field games. So these are plots of the evolution of the distribution of the state at time t, because we can compute them explicitly here when I know all the coefficient. To the paper, I forgot to include the slide where we do this calculation without knowing the coefficient of the model, and the plots are very similar, but they're not as pretty. I apologize. While preparing the slides, I missed including this one. The second example that I will give is an example, again, which is detailed in the paper, where we have state, which is the torus. So it is going to be a continuous and compact space, and the action space is the whole real line, so which is not obviously compact. and the dynamics are given by a naive, simple Euler discretization of the model that we use in stochastic analysis. And the reason why we do that is that if we take this type of cost, if we take this function cost, then we have explicit solution for the solution of the mean field control problem. And this is what we will use to compare the solution of the reinforcement learning numerical method. We will want to have something to compare it to. Okay, so in this particular case, there is no common noise, but we have an explicit solution. The stationary solution is given by an optimal ergodic control given here, and an optimal state density given here. So we're going to use that as benchmark. And now we're going to assume that we do not know the coefficient entering the equation, and we're going to let this Pdpg algorithm help us find the solution. And so you see in red the evolution of the distribution in blue over time, and the red is the ergodic one. So you see that it converges toward the ergodic solution, and you know, the learning for two initial distribution is the plot below. So it's not as smooth, but it is what it is. All right, so I think I'll stop here, and I apologize for missing one slide.
Thank you very much, Rene, for a very interesting lecture. Are there any questions from the audience?
Hello, Rene. I have one question about the last part of your talk. So you said that you approximate continuous state space by discrete state spaces. My first question is, are there any results about this? I mean, the impact on the convergence precisely of the algorithms? Can we quantify? Can we get any results? And the second question is the type of approximation that you use. So you spoke about histograms. I'm just wondering about other methods for discretizing my measures. For instance, if you work on the torus, you could think of approximating your measures by means of their. So you have a look at their Fourier coefficients, and you truncate the Fourier expansion. For instance, you just retain some Fourier modes. So these are two questions that I have. The first one about the accuracy of the approximation, and the second one is about the type of approximation that you use for passing from continuous to discrete cases.
The answer is clear. No, I do not know of any result. And to be quite candid, you know, we are taking a method which involves approximation of functions by neural network, for which, again, what we actually compute and implement is not covered by the universal approximation result, which guarantee that neural network will give you a nice convergence. I do not know of any rigorous proof, but there are several levels of approximation which are used. You know, when we want to use this actor-critic method, you know, it converges in very, very special cases. But when you put a neural network in the middle to approximate policy and value function, even then, you know, beyond approximating the continuous state space by a finite state space where we take histogram and the height of the bar being also finite, you know, I do not know of any convergence.
No, this I understand, but you could say up to some level in the analysis, I can make some comparison between the continuous model and the discrete model. I understand that once you have the neural networks, then you cannot say anything. But before this, maybe in some theoretical description of your algorithms, maybe you could compare the two of them between the discrete and the continuous cases. This was my question, maybe up to some level in the analysis. And anyway, the second question is about the type of approximation that you choose. Once again, you said that you use empirical measures or histograms. Could we think of other types of approximation just to say that they are better fitted for the numerical purposes?
I completely agree with you, and especially when you're on the torus, this is screaming for Fourier series expansion. You're playing with the periodic function, so that should be the way to do it. And for which, of course, in harmonic analysis, we have a slew of approximation and convergence result, and not only in harmonic analysis, but approximation theory as well. No, we didn't do anything serious because these models are pretty academic. They are toy models just to show that this numerical method gives something which looks like the optimal, the true solution. So Matthew wants always to have an example where we can compute the true solution to, in a sense, benchmark any numerical method. But I do not know personally of any approximation result, even though I agree with you that working on the torus with a cost involving trigonometric function, this is screaming from using a different form of approximation. You're absolutely right, but we didn't do it.
Thank you, Rene.
Are there any further questions? Yes.
Hi, Rene. Thanks for the very nice talk. I have a question regarding the numerics part. So is there any sample complexity results derived for like mean field MDP problem?
All right. The literature in reinforcement learning and all of the talks that you hear in reinforcement learning give you convergence guarantee. In earlier paper, we had some very naive rate of convergence, but very naive and definitely very far from optimal. I do not remember if we reproduce some of these this approximation result in this paper. As I said, this paper has a very painful history lasting for these 4 or 5 years. And one of the co-author is somewhere in Nature, I don't know where it is, and the other one is quarantined in Shanghai, even though he's going to speak maybe tomorrow. So you should ask Matthew, but I understand that people in reinforcement learning want convergence guarantee. Sometimes they're not very useful, but they are estimate. I don't even remember if we have some on the paper. I know that we had originally some, but they are far from optimal.
I see. Yeah, thank you.
So I didn't answer your question. I apologize for that, but that's my state of affair.
I see, because I feel it's also a very important question about like sampling efficiency. Mm-hmm.
I agree 100% with you that this is important. However, I will make myself a few more enemies in the fact that most of these guarantees which are published and pushed and advertised, yes, they are guaranteed, but they are completely useless. There are insurance policies which give you guarantee, but I would not pay for these insurance policies. And so many of these guarantee that you see in many of these papers are of this type. This is why, personally, I was reluctant to include in paper some of these estimates. But I know that we have a couple in previous papers. I do not know if we have in this paper.
Thank you.
Thank you, Rene. It looks like we don't have any further questions from the virtual audience either as well. So if not, let's thank Rene again for a very nice talk.